A social choice function receives an input and type profile of all the players and returns an outcome. Basically, it specifies a social plan, deciding which is the outcome on the basis of the actual preferences of the players. Consider this simple example. We have n players. The space of outcomes is the single-dimension compact set 0, 1. The space of types of every player is defined as the space of types in the range 0, 1. Suppose that we have 3 players whose types are θ1, θ2 and θ3 in the picture. Now we have the utility. Each player has a piecewise linear utility that has the maximum value where the outcome is equal to the type. And then the utility function decreases linearly as the distance between the outcome and the type of the player increases. The maximum value of the utility is 1. These utility functions are called single-peak utility functions. Here the social choice function. Suppose that we receive an input θ1, θ2 and θ3. The function f returns the average among the θ's received in input. Consider here another example. The setting is the same as before, but the social choice function is different. More precisely, the social choice function returns the median of the vector of types received in input. Now we focus on another example. In this case, the example is related to the auctions. We have in general n players. Suppose that in the specific instance of our example we have 4 players, the blue, green, red and pink. Furthermore, we have another entity called auctioneer that is not a player, colored in orange. The set of outcomes is equal to the set of players. The meaning is that each outcome corresponds to the player that will receive the good sold by the auctioneer. The space of types of every player is the range 0, 1. Assume that the types are sorted in the slide in such a way θ1 is larger than or equal to θ2, that is, in its turn, is larger than or equal to θ3, and so on. The utility function of player I is 0 if such player will not receive the good sold by the auctioneer, while it is the type θ of the player if she will receive the good. The social choice function returns the outcome corresponding to the player with the largest type. This means that player 1 is the winner in the specific instance reported in the slide. Here another example. The set of players is the same. The space of outcomes is more structured than before. Each outcome specifies a player that corresponds to the winner of the item and n values denoted with p. These values are payments. A positive payment means that the player must give money to the auctioneer. The space of types is as before. As well, suppose that the same ordering over the types of the player holds even here. The utility functions of the players are as before, except that here we have a new term that is negative due to the payment that the player will do to the auctioneer. The social choice function must determine both the winner and the payments of the players. The winner is determined as before, and therefore the winner is the player with the largest type. Thus, player 1 is the winner in a specific instance in the slide. The payment of player I is 0 if such a player is not the winner, while it is the type of the player otherwise. Thus, the winner, that is player 1 in the slide, pays exactly her type to the auctioneer, that is theta 1. Finally, the last example. The setting is as before. The only difference is related to the definition of the payments. More precisely, the winner pays the maximum type of the other players, that is, the maximum of all the players except herself. So in this case, the second highest type is that one of player 2. We focus on the properties of the social choice functions. The first property is efficiency. The idea behind efficiency is that the social choice function returns outcomes that are the most efficient. Since we have multiple players, the most suitable concept of efficiency is Pareto efficiency. We have different degrees of efficiency depending whether the efficiency is an expectation or not. The weakest notion of efficiency is the ex post efficiency. It requires that, for every profile of types, the outcome is Pareto efficient. A bit stronger notion of efficiency is ex interim efficiency. It requires that the lottery over the outcomes, in expectation over the types of the other players, is efficient. Finally, the strongest notion of efficiency is ex ante efficiency. It requires that the lottery over the outcomes, in expectation over the types of all the players, is Pareto efficient. Here are some examples. Suppose that we have two players, player 1 of two types, theta 1.1 and theta 1.2, while player 2 is only of one type. We have a two-dimensional space, where the dimensions are the utility of player 1 and the utility of player 2. In the plot, we have the utilities of the players when player 1 is of the type theta 1.1. All the outcomes above the dashed line are Pareto efficient, while the outcome x3 is not Pareto efficient, being dominated by x4. So, if the social choice function is ex post efficient, it returns any possible outcome above the dashed line. Here we have the same when the type of player 1 is theta 1.2. The outcomes above the dashed line are Pareto efficient. So a social choice function f that is ex post efficient can return only x3 or x4 when the type of the player 1 is theta 1.2. Suppose to consider the case of ex ante efficiency. In doing that, we focus only on the outcomes that are ex post efficient, since if we also consider outcomes that are not ex post efficient, then we cannot have efficiency in ex ante. So we are requiring that the lottery over the outcomes is efficient. We need to consider both types of player 1, so type theta 1.1 and theta 1.2. Suppose that the probability over the types of player 1 is uniform, and therefore that theta 1.1 and theta 1.2 can occur with 1/2 of probability. This means that if the social choice function returns x2 when player 1 is of the type theta 1.1 and returns x3 when the type is theta 1.2, the expected utility of that lottery is the green circle. Here we do the same when the outcomes returned by the social choice function are x1 for type theta 1.1 and x4 for type theta 1.2. We can see that the green circle in this case Pareto dominates the previous one. Therefore, ex-ante efficiency is stronger than ex-post efficiency. In particular, we have that ex-ante efficiency implies ex-interim efficiency, that in its turn implies ex-post efficiency. Here we focus on a different property, individual rationality. The idea is that every player always prefers not to abstaining from taking part in the game. Ex-post individual rationality requires that the utility of player I in every possible outcome returned by the social choice function is not strictly smaller than the utility given by the status quo, denoted with U bar. This must hold when all the types of all the players are given. Ex-interim individual rationality requires that the utility of player I in every possible outcome returned by the social choice function is not strictly smaller than the utility given by the status quo, in expectation with respect to the types of the opponents. Finally, ex-ante individual rationality requires that the property holds in expectation with respect to the types of all the players. In this case, the directions of the implications is reverse compared with efficiency. It is easy to prove that this holds. Indeed, suppose that ex-post individual rationality holds. This means that the utility of a player over all the outcomes returned by the social choice function is larger than the status quo. This means that every possible randomization over those outcomes will generate a lottery with a utility for a player larger than the status quo. The same holds in the case of ex-ante. A social choice function is called dictatorial if it returns an outcome that is always the best for a player, for a single player. And such a player is called dictator. In other terms, we can define a social choice function as the maximization of the utility of the dictator.